In this lecture, we are going to solve this problem, count total number of islands. You can also see this problem as count the total number of connected components. Here we are given a grid, but this grid we will be solving using graph and DFS algorithm. Okay, so if we compare this grid with a graph, then all the ones they can be treated as nodes, and these nodes are connected if they are directly uh, placed one to one another, either in the left or the bottom or right or the top. Okay, so if two nodes they are diagonal to each other, then they are not considered as directly connected. Okay, they are only considered as connected if they are like either horizontally or vertically next to each other, then they are connected. So we have to find the total number of island. An island is basically a group of ones, and one is a land. Okay, so how we are going to do this? We will be using the DFS algorithm to traverse through this graph, and what we will happen is basically the total number of times we need to traverse is going to the total number of islands, because each island will be traversed in a single DFS call, right? So this is one island, these are connected to one another, these are the different components that are connected to one another. So within a single call we can go through all these four in a single DFS call. This one, it is alone, so therefore in a single DFS call, we will traverse through this only. And in another DFS call, we can move from these ones towards one another. So this can be completed in another DFS call. There will be total of 3 DFS calls. Okay, so what we have to do is firstly we have to traverse through whole this grid, and we will look at the current node that we are on. Okay, so each node it can be represented using its x and y coordinate. Okay, for example, this is the 0, 0 coordinate, and here we have the node having value 1. Okay, so the 1 value represents that it's a land, so we can start doing DFS from this position. So what we will do, we will start doing DFS from this position. Why? Because it is not yet visited. Okay, and we will also keep another visited list. So from 1 we will move to this one. Okay, and then we can from here move to this one, and similarly we can also go to this one. So all of these 4 ones, they are completed or visited in a single DFS call. Now we will move forward for the next nodes, and all the nodes that are already visited, we will not look at them again. Okay, and now I come to this one particular node. It has value of 1 and it is still not visited, so I can perform a DFS on this one. So I can perform a DFS, and in this DFS call only this one is visited, because there are no other neighbors. Two land pieces which are diagonal to one another, they are not considered as neighbor. You are only neighbor if you are connected either horizontally or vertically directly. Okay, so now after performing the second DFS call, I will move forward to the next nodes, and this time I come to this one particular node, and here I see this is still not visited, and it is has value 1, so I can start doing DFS on this. So I'll again do DFS, and then I'll visit its neighbor. Okay, and in this third DFS call, I visit all these two nodes. Okay, so I did total of 3 DFS calls, and that means they are total of 3 different islands, or you can say 3 different connected components. Here we are using a single global visited set that can help us keeping track of all the different nodes that we have visited, so that we do not revisit them. Okay, and we have another variable which is called count DFS that will keep track of how many times we have performed the DFS algorithm. Since the total number of times we have performed the DFS algorithm is the total number of islands or the total number of connected components. Visually, it's showing the same thing. We perform our DFS from the position x equals to 0, y equals to 0. Okay, and we have explored all these 4. So we have formed one island, and we are inserting them in our visited set. In the next call, we are at this position. So this is the only one that is added, and we have incremented the count DFS to 2 from 1, since this is the second time we are performing a DFS call, from x equals to 2 and y equals to 2. In the next DFS call, we will be performing DFS from position x equals to 3, y equals to 3. And these are the two different nodes that will be covered in this one. So we are adding them to the visited set, and we are also then incrementing the count DFS to 3. Finally, we are done traversing through the complete matrix, and our algorithm is done, and we perform total of 3 times DFS. So the number of islands is 3, and that is our answer. Now let's solve this problem on Leetcode. Okay. So actually I have already solved this problem. So I'll reset the solution. Okay. And you can go through the problem statement. This is the same thing that I have already told. So what we are going to do is, if you have already seen my algorithm DFS video, then you know that this is how I implement. So we have the DFS algorithm, and we take graph as the first argument and the node which are visiting, and then we have the visited set that keeps track of all the nodes that are visited. So if visited is none, then we set it to set. Okay. And then we add the current node to the visited. So visited dot add the current node. And then what we are going to do, we look for all the neighbors of the current visited node. So for neighbors in, and how do we get the neighbors? We get it from the graph. For a given node, they are at the node key in the graph data structure. Okay. So if neighbor is not in, if neighbor not in visited, then what we are going to do, we are again going to perform the same DFS algorithm for that neighbor. So self.dfs for the on the particular graph for the neighbor, and we are also providing the visited node. Now for the grid, what we are going to do, let's first define the rows and the column. The rows are going to be the length of the grid, and the columns is going to be the length of any row. Let's just take the first row. Okay, so we are going to traverse through each and every cell in the grid. So for I in range rows and for j in range columns, we are going to traverse through it. And what we are going to do is we are going to look at the current cell. So firstly, we have to check if it is land or not. So we are going to perform DFS only if it is land. So if grid ij, this thing is 1, and what? It should not be visited yet. If it is already visited, then we will also not be performing DFS. So we have to check if it is visited. So it should not be in visited. So grid. So we represent each node using its x and y coordinate. Okay, so I and j are here are the x and y coordinate. So we have to check it is not in visited. Firstly, we have to define the visited set that will hold all the nodes that are visited. Okay. So if it is not in visited, then what we are going to do, we are going to perform DFS at in this particular position, sub.dfs, and we are going to provide the graph, then this one particular node, and then the same visited set. Okay. One more variable that we have to define over here is count underscore DFS. It keeps track of how many times we have performed DFS. So each time we perform DFS, what we are going to do, we are going to increment this. Okay, and in the end, we are just going to return this variable, count DFS. Okay. Now we still do not have generated this graph data structure. We actually do not need to create this graph data structure. The reason is because we know the graph data structure is used to find the neighbors for any given node. And we can already know about any given node neighbors from its top, bottom, left, and right position. Okay, so what we are going to do is that instead of using the graph, we are going to use the grid over here. So this is what we will be using. we will be using just the grid, and we will be passing the grid. And what we are going to do? Uh, Firstly, we are going to take the X and Y position for the current node. So we have to check if the current node it is in the bounds or not. So if X is greater than or equals to 0, meaning it is within the grid, and X is less than the length of grid, and Y is greater than or equals to 0, and Y is also less than the length of grid 0. So this is to check that the node that we are currently exploring, it is within the grid itself. So then only we are going to do, uh, we can now just move all of this code inside. Okay. And there are some other checks that we will also be performing. That is, firstly, we have to find if the current node is visited or not. So if node in visited, meaning the node is already visited, then we can just return. Okay. And one more thing that we can have a look at is if the current node that we are trying to visit, if this thing is 0, meaning it's water, then we will also return. Okay. If it's in visited, we will return. And if it is water, then we are going to return. If it is out of bounds, then also we are going to return. We can just make this into another. We can condition. Instead of checking if it is in bounds, we can say that if it is not in bounds, then we are going to return. So if it is not in bounds, then what we are going to do? We are going to return. Okay. Now, what about the neighbors? We know that there can be at most 4 neighbors, okay, for any given cell. So we are going to visit all the 4 neighbors, and they are either we can move to the left, okay, so self.dfs, then we will pass the grid, and the node is going to be uh, x is going to be the same, but it's going to be y minus 1, and we can move to the right, okay, self.dfs grid. This is going to be x, y plus 1. And one thing I forgot is I have to also provide the visited set, right? Then we have the top and the bottom. So for the top, we are going to decrement x coordinate, and y is going to remain the same. This is for the top, and then for the bottom one, we are going to just increment the x coordinate. Y is going to same. Okay, so these are the 4 different calls that we have to make. And in the base condition, we are already checking if the calls, we have made these calls without checking if those coordinates, they are in the water or they are within the bounds or not. If they are out of grid, then what is going to happen? So all of, and if they are already visited, then what happened? So all of those things, they are actually covered in the base cases. Okay, so therefore we do not have to check over here that we have to only make these calls if the particular y minus 1, this coordinate is within the grid, and this is 1, and this is not visited. All of those checks, they are made in the base conditions. So let's just submit this solution. Firstly, we will try to run the code to see there is any problem. So there is some indentation error. If visited is none. So here we have indentation error, and I have fixed the error. Let's rerun this code. Node is not defined. Okay. So node is not defined here. we have to first define what node actually is. So node is actually the I comma j coordinate. And here we can use the node. Let's rerun this code. And again, we are getting some issue. List index out of range. Grid x comma y equals to 0. So here x and y, they are going out of bounds, and we are checking, and it's saying that these variables, they do not exist. So actually we have to perform this check first, and then we can check for its value. Firstly, we have to check that the x and y coordinates, they are in bound. Again, we are getting a similar error. So if x is less than 0, sorry, this is not and, this is or. If any of these condition is true, that means the element is going out of bound, it is out of grid. So therefore we have to return. Our solution is now accepted. So let's just submit to check if it is accepted. Okay, so this solution is valid and it is getting accepted. Let me walk you through once again through the code. So we are firstly getting the rows and the columns, and we have taken a visited set to keep track of all the different elements that we are visiting, all the different nodes that we are visiting. We have the count DFS to keep track of how many times we are performing the DFS. Then for each node, we have to first check if it is has value 1 or not. If it has a value 1 and it is not visited yet, that means it is not in the visited set, then we are going to perform the DFS algorithm. And each time we perform a DFS algorithm, we are going to increment the count DFS. And here is our DFS algorithm. Here we are firstly checking that the current node on which we are performing the DFS, is it within bounds or not. If it is visited, then we return. If it is out of bounds, then also we will return. If it is a value 0, that means it's water, then we also return. Otherwise, we will visit the current node, and we go to the left, right, top, and bottom uh, uh, neighbor to visit them using DFS. So this was all it.